Okay. Let's pick up where, well, let's start by seeing if you have any questions. Is there something that we need to talk that we need to talk about at this point? Some point of confusion or any questions that you have? Let's see, last time, here's the announcement for the canceled lecture. Let's see, last time we talked, we went into assignment 1, right? We talked about this. In fact, after I did that, I realized that I didn't want to do that. Actually, this is something that you need to work out by yourself. It's not like a lab. In the lab, I'd like to show you how to do that. We do it together as much as we can in this context, and then you go off on your own and try to reproduce that and vary it and experiment and try to learn that way. But the assignments are intended for you to work on by yourselves. And they're also designed to look like the quizzes in the final. So I worked through a bunch of exercises last time, so you'll need to go through the remainder of those exercises on your own and then submit your responses to those through Blackboard. So in Blackboard, you'll in fact type in some answer to the text boxes that are presented to you for this assignment. All right, let's take a look at Lab 4 then. Did we do Lab 4? No, we did not. Okay, so let's go ahead and get that. There are lots of work to do in Lab 4. So let's go ahead and do it. Let's make a folder, Lab 041, and let's add the new folder to the repository. Let's copy a main file from somewhere else, just as a starting point. Let's go ahead and add that to the repository. There we go. And let's, you know what? Let me do this. So we can build and run that program, whatever it is. Oh, we got to get out of there, right? Okay. Let's take a look at the what we're asked to do, factoring. Write a console program. That's all we ever do in here, console programs, that asks the user to enter a positive integer. The program computes the prime factors of the number and prints them. For example, if the user enters 100, the program displays 2255. Let's implement that, and then we'll come back and read the rest of it. So prompt the user to enter a positive integer and then compute the prime factors and print them. All right. So it's a positive integer. We're going to need an integer. We'll call it, say, n. Now we're going to ask the user to enter a positive integer. And we'll read that integer in right here. Then we'll compute and print the prime factors. The prime factors of n are We'll do it like that. Then we'll list them. And listing them will look something like the following. You know, we'll have a bunch of Couts in here. You know, maybe 2 is a prime factor. And after we list that, let's put a blank here. And then maybe 3 is a prime factor. And then when we're done that, let's print this this new line here. And this little text in here, I could put that in there. We have it. So in case the user enters in a bad integer, if the user enters in a bad integer, what we did before is we had a loop, right? We just kept them to keep trying in a loop. I mean, we could do that, or we'll just terminate. Like when I terminate, I'm just going to return. See, but I'm returning a 1. That's because it means like a failure. But I think 1 is not user. It's not usually user failure. It's usually some sort of system failure, like the disk drive crashed or the network is not available. So normal termination, you usually return a 0. So let's return a 0, even though the user failed to do their part. So let's go ahead and see if we have the shell of a solution ready at this point here. So I want to run that, enter a positive integer, 6. The prime factors of 6 are 2 and 3. In fact, that's right, isn't it? But of course, if we enter in 9, we still get 2 and 3. So this solution is only good for one number. This is a little tricky, you know. I'll do that later. That's a little tiny detail. Okay, so how are we in fact going to do it? We don't know how many numbers we're going to print out. Right? What if we enter in a 16? We're going to print 4 2s. You know, if we enter in a 7, we have to go to print just 7. So we don't know how many prime factors we're going to end up getting. So you know there's going to be a loop here. And there's going to be some kind of a loop with a loop condition. Let's go ahead and just visualize the answer using this approximate code. There's going to be something like, we're going to iterate. We're going to say, oh, I can figure out one of the prime factors and print it. All right. Let's see if we give any hints in here. Develop 8 test cases that verify that your program runs correctly for them. The test cases should contain some prime numbers as well as non-prime values. So we need 8 test cases. Include the test cases within a multi-line comment in your program. Make sure the comment is nicely organized and easy to read. Right, 8 test cases. That's easy to do. Let's go ahead and do that. And let's put it in here. Here's a multi-line comment. And something like this program computes the prime factors of a number provided by the user. And these are our test cases. So let's suppose we have like the prime factors of 6 are 2 and 3. We want 8 test cases. What do I have there? I have 6, right? There's 8 test cases. Now we just need to change the numbers around. The prime factors of 2. You know what? We better, because we might just get 1, so I don't want to use the verb are. Let's do it like this. And let's get rid of the periods. I don't want to have to print that out. The prime factors of 2, just 2. Prime factor of factors of 9, that will be 3 and 3. Prime factors of 27, 3, 3, and 3, like that. And what are some other good ones to use? Say, let me try 11. This should just be 11, right? Any suggestions for test case? See, we want to break the code. So we want to try to pick numbers that are going to stress the logic in our code so we can find bugs. That's the purpose of the test case. 74? Yeah, 74. Okay, what are the prime factors of 74? 2, we know that, right? Because it ends with an even number. So what's that? 35, 37? 37 is prime, right? Does that look like a good one? Yeah, that was a good one. All right, let's pick another one. Another one. How about something with 108? Yeah. What's 108? 2. That's 54. That's another 2. That's 27. Yeah, 27. And that's 3, 3, and 3. That's a lot of factors there. Okay, that one should break it, hopefully. Okay. And we'll pick another test case in a moment. Let's leave that open. All right. So, there's a what we do is let's do it like this. I mean, because I've done this before. Okay. So unless you want to have a suggestion, a brainstorming session here, but I already know the answer. So, but any suggestions? How would you go about doing this? We got to have a loop, right? I'll tell you how that I've done it before, and I mean it's nice to work these things out on your own. We don't have time to do that. We got to plow through the material. That we have this number n, and let's just pull numbers out of it. So let's start at a small number. Let's start with 2. Let's pull as many 2's out of n as we can, and then go to 3 and try to pull out as many 3's as we can, like that. Okay. And so while n is greater than one, not sure yet. Let's just see if that works. Well, n is greater, so we're going to keep reducing n down until it gets to 1. And let's take a look here. So what we'll do is we're going to try every number from 2 to n. Now, this is not, I'll tell you what we're doing here. We're not doing an efficient solution. We're just going to do the simple, naive solution. It is not going to be the most efficient. So, we'll solve the problem in a simple, naive way that gets the job done for us. And a more complicated solution that can factor very large numbers more efficiently, that's a subject for, say, for an advanced course on algorithms or number theory, something like that. Okay. All right. So let's do it. So let's do the remainder here. So we have, if we take n and divide by some value I, an integer I that ranges from 2 to n, and then we get a remainder. So that's the remainder operator right there, called a modulo. So take n, divide by I, and take the remainder. And so then we look, if the remainder is 0, we've got something. We've got a factor. And if I is a factor, we print it out. Right? And we take it out of n. Oops, not 2, but I. So in other words, I divides evenly into n. Let's go ahead and do that. This is integer division. And then we continue. So we try every number from 2 to n. How are we going to try every number from 2 to n? What construct are we going to use there? We use a for loop, because we know a start point, end point is perfect for a for loop. We're going to try from 2 to n. And we'll just increment I, right? Oh, we could add 2 to it, couldn't we? That would save us a little bit of work, but not going to do that. All right. That means all of this logic here is contained within that for loop. And this is very important to keep track of these indents. Yeah, these are very important. This shows that how certain blocks of code are dependent on conditions. So this whole block of code here only gets executed when the loop condition is true. That's the condition. This is the loop condition. When this condition is true, that block of code in those braces will be executed. This is a block within the block. That's a subblock. That subblock of code will be executed when this condition is true. So the indentation is used to show the human eye those dependencies. The compiler doesn't need to know that. And you're required in this course to use indentation to correctly express those dependencies. Question?
What's the difference between where it says integer remainder n in the percentage
Yeah.
line, and then the bottom it says n divided by or divided by?
This, you know, when you take a number like say 3 and you divide by 2, you get a quotient and you get a remainder. So you're doing one operation, but you're getting 2 results. So this is divided by. This is divided. They're both divided by. It's the same operation. It's just that this operation, you take the remainder instead of the quotient. And this division down here, you take the quotient and toss out the remainder. All right? They are, in fact, both divisions. But they retain a different result. Okay. Now, we have this piece of logic here which reduces n. So, you know, when you have a loop that looks something like this, you better make a quick mental check that, wait, n's got to get small somewhere here. And in fact, this is where n gets small. But if this always remains false and n never gets small, then we're going to enter into an infinite loop. So that's the kind of thing you've got to look out for when you're crafting this type of code. So we have the value n, and we're going to pull factors out of it one after another. We're going to start at 2. And now notice, oh, look at this. Let's suppose we have, if we have 4, if n is 4, then 4, and we start at 2, and 4 divided by 2 gives us a 0 remainder. So this will be true. And then we'll print 2. Then we'll convert n. We'll take 4 divided by 2. We'll get 2, and we'll put 2 into n. And then what do? And then we increment I. And I is now 3. And 3 is not less than or equal to n, so we exit. And we just have 1, 2 printed. So this logic isn't good enough. We can't even factor 4. So let's think about what it is that we're doing wrong here.
We should start over back at 2.
Yeah, and that's why I'm going to kill this for loop altogether. I don't even like this solution anymore. Not happy with it. Because if we had 8, for instance, we want to stay on 2. We just want to keep trying 2 till we're tired of 2, then move on to the next number. So let's do it like this. Let's try it like this. Let's start with an I set to n. Oh, sorry, I set to 2. We'll try the little number first. And then we'll have a condition here. While n is bigger than 1, we got to do something. When n gets to 2, we still need to do something. And here we try the division here. And if we get a divisor, then I is good. We're going to print I. We're going to take I out of n. But we're not going to advance I, because we want to try 2 again. So, and if when we come back up to the loop condition, n is now 2, it's still bigger than 1. And we take 2 and divide by 2. That gives us a remainder of 0. And we're going to print 2 again. Then we're going to take 2 divided by 2. So n becomes 1. Now the loop condition is false, and we're done. So I'm happy with this. Well, what happens if the number is 6? If the number is 6, if n is 6, let's go through that logic. Let's suppose n is 6. Then we take 6 divided by 2. Remainder is 0. We print the 2, take 6 divided by 2, that gives us 3, n is set to 3. Come back to the loop condition, 3 is bigger than 1. Okay, 3 is bigger than 1, we're not done. Take 3, divide by 2, the remainder is 1. This condition is false. So we don't do this, and we just go back up here again. When n didn't change, n's not getting smaller, now we have an infinite loop. See, if this is, well, I mean, the solution is here. So we have an else, you know, if the remainder is non-zero, it means the factor that we're trying, the I that we're trying, we're done. We've tried to divide it into n as many times as we could. It's no longer working. That I is bad I. So, or it's no longer useful anyway. So we're going to increment that I here. Now we're going to try the next I. So that when we do this division here, we're going to try 3 now, using that example that we just looked at. Let's just do a mental check here. Let's suppose we have the number 5. 5 is a prime number. So we should just, if we input 5, we should just get 5. Okay? Or 3. Let's go easier. 3. Or 2 even. Right? Let's do 3 first. Because 2 is a special case, because that's where we start the process from. Let's try 3. 3 is bigger than 1. So we take 3 divided by 2. Because remember, we start I at 2. So we take 3 divided by 2, and we get 1. So we're going to increment I. I becomes 3. And n is 3, so the loop condition is good. We're going to take 3 divided by 3. We're going to get 0. This remainder is 0, so we're going to print the 3. Then we're going to take 3 divided by 3. N becomes 1. The loop condition is now false, and we exit. So that works. I think we got it. Think we got it? We could try 2. 2 is a special case. By the way, I didn't even talk about 1 yet, right? Because I can't even remember. Is 1 a prime? It's not a prime, right? So this 1 is going to mess everything up. So we kind of have to add some logic at the top of the program to check for 1. Did the user enter a 1? Because I think if you look at the definition of what a prime is, 1 is. Who knows? Math majors? Is 1 non-prime? Can you do research? Find out if 1 is non-prime? Huh? Because like if we put n, we set n to 1, the loop condition is false, and so the prime factors of 1 are, and then we get nothing. Actually, that's right. There are no prime factors of 1. That's it. So it does it right. There are there prime does 1 have any prime factors?
No, it's not a prime.
If 1 is a prime, it has a prime factor.
Right.
But it's not a prime, right?
Right, it's not a prime.
So actually the code runs correctly. I mean, we don't
Isn't it a prime? 1 times
ask
1.
those math people. I don't know. Anybody know that? Okay, anyway. Let's get back to I think this is going to work. I'm really optimistic about this. I think it's going to work. All right, let's be disciplined. Let's go back and look at our test cases. Let's try 6. Well, it still says R. You know what? I don't like that. Let's do this. Let's get rid of that R.
Are there any header files we need? No, right?
No. And we don't have any assertions, so. So we got 6. What's the other test case? Let's try 2. Let's try 2. It still says R. Oh, you know what? I didn't compile. Did I? Maybe did I compile? Maybe I didn't save. I don't know. Oops. Sorry about that. I'm trying to catch up for that lost 15 minutes, you know. Okay. Let's try 2 again. There we go. That works. Okay. 9? Okay, good. Let me know what the test cases are. 3 and 3. 27. Whew, that was a good one. That was 11. 74.
108.
108. Got it.
And then you didn't get the last
And then we need a last one here. And let's 69. There we go. These are small numbers. These are small numbers. Is that right? 3 times 23? Yeah, of course that's right.
How do you get it to like keep letting you type names? I mean,
Put the whole thing in a loop if you want.
oh, okay.
Just make another, enclose everything into another loop. All right, we have finished this. Let's commit our work. There it is. So nothing was transmitted until we issued the commit. Do we have time? Yeah, we do. Make directory, lab. So we, I just went through and did the normal subversion business. Now we're in here. And this builds and runs. Okay, good. So we have our, I just made a copy. Let's go ahead and solve the next problem. Prime numbers, more of the same thing. Write a console program that reads a positive integer entered by the user. The program computes and displays all the prime numbers between 2 and the number entered. That's different than printing the factors. This is just, I'm going to print a sequence of prime numbers all the way up to the number that you gave me. To solve this problem, you need to nest an inner loop within an outer loop, which we did already, right? We already showed how to do that. All right. And I didn't ask, did I ask for test cases? I didn't ask for test cases, did I? I should ask for test cases. I'm going to put that in there. Whoops, no theme there. All right, let's go ahead and do that. So the test case, it'll look something like this. If we enter in say n, that like 10. Then we should get the numbers 2, 3, 5, 7, and that's it. And if we enter in say 13, then there should be 11 and 13.
So it's greater than or less than or equal to?
Is it said less than or equal to? What's that? get that wrong? Between, so between 2 and the number, yeah, I don't matter that much. All right, let's do this. So enter a positive integer. And we have that. The following numbers are prime. Yeah, then we're going to have the loop here. I think this is going to be a for loop, right? Because we know that once again there's more efficient ways of doing this. Maybe we're going to start at 2, and we know that that's prime. And while I is less than or equal to n. Well, we're going to go to the next number. So let's try every number I between 2 and the number entered. So we've got our loop. So it's going to look something like this. Let's pretend every number is prime. All right, that's what it's going to look like. But we need to remove the 4, the 6, the 8, the 10, and the 12. You see how I'm doing this like incrementally, just doing one step at a time? Get something running. Get a prototype running right away, and then try to build it out from there, one step at a time. Okay, so we have to decide. You know, it's like this. You know, if I is prime, then print it. So how are we going to decide if I is prime? Let's do this. Let's do the simple way. And, you know, I is prime if nothing divides into it evenly. So let's try to divide every number into the number, up into, you know, so if we enter into 6, let's try to divide 2, 3, 4, 5 into 6. And if one of them divides into 6 evenly, we know it's not prime. And we can try non-prime values as well, so we can just keep it simple. So we've got another loop here. We'll call this J. Maybe I'll use K. I'll use J, I guess. Let's start at 2. And while J is less than n, the number. Sorry, not K. Yeah. So is I prime? There it is. So we want to know if I is prime, not n. We don't care if n is prime. We want to know if I is, so we're going to try, we want to print every number I that's prime between 2 and n. So when we have a given I, we're going to let J range between 2 and I minus 1. And then we've got some logic in there like this. We're going to do just like before. We've got this remainder, and we take I, and we try to divide it by J, and we toss out the quotient and just take the remainder. If the remainder is 0, we know it's not prime. So let's not bother doing that. Let's continue on. So we know that it's not prime here. What is it? J. Oh, I'm sorry. Because we found a j that divided into I, so I is not prime. We know that I is not prime. And if we do this whole loop without going in here, we know that I is prime. So if we found one j that divides I, then we know that I is not prime. So if we don't find any j, so we're going to use a Boolean variable to track that. We're going to say that we're going to create a Boolean variable, which is it's a variable that represents either true or false. And we're going to say I is is frozen. Oh, there it is. I is something is crashing on me here. Network problem. Maybe they're rebooting the server or something like that. We have lost this connection. Oh, there we go. I is prime. We're going to be optimistic. We're going to say yes, I is prime. This I, we're going to set I to be 2, then 3, then 4, like that. And each time we're going to start with the assumption that it's prime. So we express that assumption with this Boolean variable, is I prime. I is prime. We're going to set it to true here. So here, this is the point where we know that I is not prime. So that's the point where we set that Boolean variable to false. This is where we discover the fact that contradicts our initial assumption. And if we can go through this loop, if we can range j between 2 and I minus 1 without ever hitting this, then the variable I is prime will remain true when we exit the loop. So that means that variable I is prime, we can use that to decide whether to print I or not. Any questions on that? Oops. Let me bring it to the top. It works. I don't think we need as many test cases. You know, we could, we're running out of time here, so let's just stay with 2. Any questions on this one?
Can you show the bottom real quick, please? The if I is prime. Cool, thank you.
I want you to sort of memorize the whole process. You know, the way I'm reading the code and checking it and thinking. Just that whole problem-solving process is what I'm trying to convey to you, not this particular solution, right? So if you can set aside my solution and try to reproduce the reasoning process behind what we developed, that's what you should be practicing on your own. Okay? Don't just read what I wrote, type it in, run it, submit it, and say I'm done. You're not going to learn much that way.
Right.
Okay.
No, he's right, man. Because I was reading this book, and that's why I learned what the book says. I tried to play around with it, and then now I know.
But there's a party Friday night, right? And you got to get this done by the deadline. All right, let's commit. All right, we got it in there. Oh, I even committed it, even though that's not done. Okay, let's see if we can. I don't know what the next problem is, but I want to let's see if we can get it done in 10 minutes. We have 10 minutes, right? Is that right? 10 minutes? I don't know what I'm doing here. Lab 4, 3. I'm there. Okay. Good. Random colors. Write a program that generates a web page that contains a list of 100 random RGB color values. The program should write something like the following into Cout. So we did a problem similar to this already, right? We already have a program that generates random numbers. Do you remember the name of that lab?
Lab 033.
33?
Yeah.
Lab 033. And let's start there, okay? So that's a better starting point than prime numbers. All right, there we go. So we have this stuff already. We got a lot of this done. HTML color values are specified using hexadecimal notation. Therefore, you need to generate strings with 6 characters, where each character is randomly chosen from this set. So see, this is an example here of a string that you need to generate. 6A3125, or this one. This one has an F in it. You won't see a G, because G is not used to represent hexadecimal numbers. Hexadecimal numbers at the base 16 means you got to have 16 digits, right? In decimal numbers, base 10, that's what we normally work in. We've got 10 digits. 0, and look, counting starts at 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 digits. For hexadecimal numbers, you start at 0, and then you count up to 0, 1, 2, ... 7, 8, 9, A, B, C, D, E, F. Those are your 16 hexadecimal digits. So just like decimal digits, you put them in a sequence, and they represent, they count the number of, this is the how many 16ths there are, and this is, what is that, how many 16 squares there are, and this is how many 16 cubes there are. It's just like decimal numbers. Okay, so we need to, what we're going to do is we're going to generate, this 6 will be a randomly generated value, and then we generate another one, and we generate it from this set. The set starts at 0 and it goes up to F in that order. So we can use this expression to get a random integer between 0 and 15. And you need to define a loop within a loop. These should be random. You don't hard code your answers. It should be random. Seed the random number generator. All right. Let's go ahead and do this. Let's look at the logic we already have. We're seeding the random number generator. We did this already. We print this stuff that makes up the web page. Then we go into this list, and we're printing a random value. But here, what we want to do is to print is to do something else. What we want to do is print a random string. So this is going to be our hex. This is our hex string, and it'll look something like, one of these examples here, like this.
You changed 106, right?
100 to 6? Is that what it? No. Is that 6? I want 100 random RGB values. Yeah. We're sticking with 100. And but actually, because we don't want to see we'll leave it at 100. So the HTML is a little bit more complicated. Let's take a look at it. It's got this style attribute in here that looks like that. And I'm going to put that in there. This is going to get a little complicated looking. So, see, what we want to do is we want to print quotes. We want to print the quotes. So to do that, we want to include quotes in the string. So we need to escape the quotes, and we use a backslash for that. That is common everywhere. Almost all languages, modern languages, use the backslash to escape the special character that terminates, that delimits strings. So this is something that you will come across. And so that is inside here. It should look like this. This takes a bit of thinking. You need to think through that's in fact what we want. And this will be the hex string. So this, what is this down here? Oh, this is the junk. Here. There it is. You see, we've got this, but this value doesn't come from that hex string. What we need to do there is to insert the hex string here. So we break this off, and we need to place the hex string inside here. And that's pretty crazy looking right there. So now if we generate different hex strings, like put a 7 there, that will come through correctly. I know we're running out of time here. We won't be able to finish this. When is this due? When is Lab 4 due? This is February 8th. And I got to check my calendar here. So February 8th, I will be back. So we can still finish this on Monday, February 6th. You'll have time to get it done by February 8th. All right, so we will continue in the next class. Friday lecture is canceled. Sorry, Wednesday lecture. Friday, that's the day of the party, right?